to thank Michael especially for the kind invitation to this nice place here and to this conference. I want to speak about dual-based methods for stabilization and optimization of nonlinear dynamics and optimal control of these processes. So the plan of my talk is the following. I first introduce the problem statement and shortly repeat the notions of asymptotic stability and stability of dynamical systems. And then I like to apply what I call duality theory. I can say this is some kind of Kara-Deodori, Hamilton-Jacobi theory in calculus of variations and optimal control. And want to point out different formulation of dual problems and the use of these or this dual problem at one point from the theoretical point of view, and on the other to get sufficient conditions for optimality, and on the other side for a numerical approach to find the optimal solution of these problems. I give a well-known application, and I consider a generalized Lotka-Volterra model where I can apply the pseudospectral method for the dual problem. So let me state the problem. I like to point out that we have different difficulties here in the problem formulation. So the one is that we have an independent variable on an unbounded domain. So let me say we have here an infinite horizon problem. And I later discuss also the problem of which integral we use here. Do we use Lebesgue integral? Do we use Riemann integral? Do we use something in between, which is called Henstock-Kurzweil integral? So we have a lot of notions for this integral in the setting of an infinite horizon. The second, what I want to point out, that I also like very much Banach spaces. So the challenge is to stay with this infinite horizon problem in a Banach space setting, at least for the state variables. Therefore, I introduce here weighted Sobolev spaces. Weighted Sobolev spaces I learned from Alois Kufner from Prague, and he introduced this for PDE systems, for potential problems in the outer domain, also an unbounded domain. We have the usual nonlinear dynamics, and we have usually control constraints for the talk. I assume that the U is a compact set in Rn and initial condition. So then altogether we have two weights in the formulation. The one is here in the objective, and the another one is in weighting the space. And both weights can be different, can be the same, can be proper weights, and can be density function. More I explain later. What interpretation we can have for the objective? So we have economical interpretation, then this new tilde is a discount rate for economic growth model. And of course, we can have also here proper weights in the state space. And the reason for the introduction of proper weights is given from asymptotic stability. I explain later on. So let us stay for a short moment in weighted spaces. So we have a weight function, which is a positive function. Those inverse function is locally Lebesgue integrable. And for a density, we additionally assume that the weight function can be integrated. The Lebesgue integral is finite. So to say shortly, we use in all settings the Lebesgue integral, not improper Riemann or some different stuff. Then we have a weighted LP space of those functions where the integrand to the power p weighted by density or weight function is smaller than infinity, and a corresponding Sobolev space where the functions are measurable functions. The function is in the weighted LP, and the generalized or distributed derivative is also in an LP space with the same density or weight function. This is our nice space to stay. It's very, very nice, especially in the case for p equal 2. The weighted space is a Hilbert space with this weighted scalar product, which is given in this way. So that's our way to solve the problem. In the problem formulation, we do not use any convexity assumption, and in case of failing this assumption, we make a relaxation, also we make a Young measure relaxation or gamma convexification in the problem, and a lot of work has to be done to show the equivalence of different relaxation in the case of unbounded domains. But this is not part of my talk. I mentioned the Lotka-Volterra model, so we consider one of the simplest nonlinear model where we have a nonlinear interaction between the two spaces appearing here in the dynamics. So this is non-linear, and we consider the control, which is affine in the state. So we have a product from state to control variable here, which is a natural assumption for a radiator model, which is controlled by the min as a super radiator. What can be an objective for this dynamical system? So its typical application is to ask how we can exponentially stabilize this system toward the uncontrolled equilibrium of the system. So stabilization is one of the main goals. Another one can be optimal control. Of course, the system over the infinite horizon, but consider as kind of restrictions those trajectories which are exponentially stable. So I think this is interesting to interact between optimality and stability. And there's a nice consideration, of course, if we have the notions of stability and the interactions with weighted Sobolev spaces. So I shortly mention the old definition of Lyapunov stability of a dynamical system here, uncontrolled. So we say that the equilibrium is stable if the states stay in a bounded domain, if they start in a neighborhood with some delta from the initial point, then it stays all the time in a neighborhood of the state. So this is Lyapunov stability. If we have additionally that for t, the independent variable to infinity, this limit is 0. So exponentially and asymptotically stable processes, so the difference in the norm vanishes at infinity. But also not a bad assumption to have it. Exponential stability is even stronger, and we find out that the equilibrium is exponentially stable if the difference of the processes goes down with an exponential rate here, e to the minus beta 0. So I'm interested mostly in this exponential stabilization of the processes. So here is the connections from stability to weighted Sobolev spaces. I take an X from this weighted space, which norm is bounded, and for the weight function, I choose e to the beta t with beta greater than 0. Then it comes out that the x is exponentially stable. So we have an estimate for x from a compact ball that the x of t goes down exponentially with rate a to the minus beta half times t. So this is a nice, we can say that this is a nice point-wide estimate of the states. Also in the finite dimensional case for fixed t, we can have such a nice approximation or a nice estimate. This comes finally from a property which I call Poincaré type inequality. If we have a function which is in the weighted Sobolev space with this weight, is a density function here. It's a density function, so we'll make the neighborhood bigger. Then we can estimate the L2 norm of the space against the L2 norm in this weighted space for the derivative. So this is often used in analysis to estimate the norm of the state against the norm of the derivative. And finally, to have a connection with usual Sobolev spaces, so this is the space of absolutely continuous functions on an unbounded interval, and we have that one function is weighted by nu, and the other one, the y function, is weighted by the inverse weight, 1 over nu of g. Then the product belongs to the usual Sobolev space. This is also nice, and from this we know, of course, that x times y is tending to 0. So nice properties and connections with stabilities and weighted Sobolev spaces. I like to mention a method to generate stability, which is of course very well known, and this is Lyapunov's first and second method. So a process which is described here is asymptotically stable if I can find a so-called Lyapunov function, which is in this earlier paper continuously differentiable, and it's 0 at the origin. And then we have this kind of condition that the total derivative of v, this we can calculate, that's the gradient of v times x prime, which is put in here, is less than 0. Then we can say that the x process is exponentially or asymptotically stable. So the Lyapunov function is used to test whether the system is asymptotically stable. For problems in mechanics, this has a well-known interpretation. So the function v is an energy function. So this expression says that we can reduce the, for functions fulfilling these properties, we can reduce the energy to bring the system asymptotically to 0. So this inequality says that the gradient is smaller than 0. Let me mention that is, of course, in the case we have here the function x, it's a partial differential inequality, and the hint is not to solve PDEs or inequalities, but have a stronger estimate for all state variables psi. So this gives reason for an optimization problem to solve. So this I mentioned here. It's not necessary to find the solution of partial differential equations. And finally, let me mention that we have, of course, also control system. Then a similar notion can be introduced also for control systems. I mentioned the method of Lyapunov, which of course has a difficulty to find the Lyapunov function. And it's not clear at all how to do it in a very general setting. Therefore, there are several concepts to construct or to construct an optimization problem to create a stability and controllability. So this was given by Kalman, and I mean nearly at the same time by Lyotov. And the idea is, for the first step, to have controllability, finite controllability, to have here an integral. This is the function here appearing in the objective. And then we have for the endpoint a certain, let me say, Lyapunov expression here to estimate the final state. So we take this problem, and beside this we have the usual differential equation here, starting from a point psi for x at t0, and taking controls in a bounded and fixed domain U. The function L is assumed to be in C2, non-negative, and the second derivative, of course, of this function has to be strictly positive. And it was mentioned in this article that the upper bound of this integral, the T1 here, can be plus infinity. And this is the difficulty to be not so much correct in the notion of the integrals. So let me say more precisely, if the T1 is finite, we stay, for instance, in the classical Sobolev space, take controls from L infinity, and all is fine. what we can do if we interpret this as an improper integral. So studying the limit for if the upper bound is going to infinity. Then we arrive, and this was done in many publications, in the space of locally absolutely continuous functions. But this space is not a Banach space. It's only a locally convex topological Hausdorff space. And is, for my opinion, not so nice. So our approach is now to take this as a Lebesgue integral, as I said, and take here a weighted Sobolev space for the state and a weighted L2 space for the control, and give a formulation of the optimization problem. If I like to mention here very general right-hand sides of the differential equation of the dynamical system, I have to make sure that the system lives over the infinite horizon. This is also a challenge since not every function f is a good function to have this property. Altogether, we have the following table which I like to point out. So we have in the model of Kalman and Vlotov the improper Lebesgue integral. We take here the Lebesgue integral. We stay in a Hilbert space, in the weighted L2 space, and for the state and the control. Depending on the integral notion, of course, we have, coming from economics, different optimality conditions. So we have overtaking optimality, weakly overtaking optimality, and some sporadically catching up, and some other criteria. And here we use a global Lebesgue criterion, which compares the integral over the infinite horizon. The ideas and the notions for the case of problems of this type with improper integrals are given by Carlson and Weiser-Rovich, and here we have some contributions in our group in Corpus to this setting of the problem in Hilbert spaces. Now I come to the next part of the problem. I construct a dual problem. This is, let me say, the idea goes back, I think, to Kara-Diodori. But there are many authors have contributed to the introduction of generalized duality schemes. Krotov did it, and we have also the contribution of my teacher, which was Rolf Klötzler in Leipzig, who constructed very general dual problem. For that, we take the admissible domain with the state equations, the contour constraints, and the initial conditions, and make a partition of this set as an intersection of two sets x0 and x1. Then I define a very general functional, and only to have an idea, I say this is the Lagrange functional. So it can be the Lagrange function. So then I have the original variables, and the y form the dual variables, and then I have an equivalence to show. So the infimum of the original problem is the infimum of larger z x0, supremum of this Lagrange functional with respect to s in y, and then we have this sign. This sign holds all the time. It's easy to prove, and therefore we have a very nice dual problem, which is the interior expression here. And duality we have in the weak form, that the infimum of the original problem is bigger or equal to the supremum of the dual problem. So this is a weak duality relations without having here the equality sign, which is challenging. And we have a lot of degrees of freedom for choosing the y here, this function space, and the general Lagrange function. So the idea is now to give examples for the construction. And the first one is, let me say, the Lagrange formulation. So for the dual variables, the functions from the y space, I make a linear ansatz with respect to the state variables here and a function y. And the function y is now in our setting also from a weighted space. So, and the idea is to add this Lagrange term here. This is the scalar product in the L2 space without weighting, and we have that this form, which appears here, is a bilinear form with respect to the state variable weighted by e to the beta t, this plus beta, and 1 over nu of t. So you have the inverse weight here. So take the dual variables from the space with an inverse weight. Can work and works. So in this form we have one formulation of the dual problem. There's a deep connection, of course, to the Hamilton-Jacobi theory and the duality for I have not enough time to explain this more precisely. We can compare this and can construct also a dual problem with the help of the Hamilton-Jacobi theory. So this is more or less also a classical approach where we have here the defect in the Hamilton-Jacobi inequality, and we have this. The Hamilton-Jacobi inequality has to be satisfied here as a side condition for the dual problem, and the function has to be zero at the optimal trajectory. So this is more or less comparable with Lyapunov's idea. So this is the old idea of Lyapunov in the setting of the infinite horizon. Let me fit all this together. We have different statements for the dual variable, which you can use. Of course, we used here, following Lyapunov's idea, also a linear approach in this function, but we can use also a quadratic term for the dual variable, which is also interesting and delivers with some functions q, which is to find sufficient second-order optimality conditions for the original problem. Now I come a little bit to the application, and therefore I want to point out that I have integrated versions of duality. So we can use spectral methods and Gagliardian methods, and we can use, of course, also a pointwise formulation, Hamilton-Jacobi inequality, which arrive finally in parametric optimization problem. Where are the difficulties of the problem goes in? So the one difficulty is the smoothness of the Hamiltonian function. This is a serious problem if we have control constraints, of course, and we have to show independence of the objective if this property is satisfied. An additional difficulty is coming from integrability, and we have to require that the defect in the Hamiltonian inequality or equality need to be integrable over the infinite horizon, and this is a challenge also. This is applied also to a nonlinear model, and we want to give an idea which function we use for the dual variable. This should be a nonlinear function which is used in the duality setting. And to get an idea, we look for the older papers of Lyapunov and also other colleagues, so we see that we have such a logarithmic function which has to be used in the bilinear case. Should I stop?
Yes.
Stop?
Yes.
Okay. This can be done if I have enough time, and this was done. And let me only shortly mention that we now have a dual problem in a weighted space with a density function. And we are in a Hilbert space, so we use Hilbert space methods, approximate by generalized Laguerre polynomials, and solve the dual problem by the pseudospectral methods. And if you are interested, I can show you nice pictures. So this is a nice method, converged very nice for linear quadratic problems. It works very well and is very sparse method. Thank you very much.